Hello and welcome to today's lecture on congestion control in packet switch networks. In the last two lectures, we have discussed about the routing techniques used in packet switch networks. So, after routing, another very important aspect that has to be considered is the congestion in the packet switch network. And here is the outline of today's talk. First, we shall discuss about why congestion arises at all, then the common causes of congestion, or in other words the sources of congestion, we shall discuss about it, and whenever congestion take place, what are the effects of congestion on the packet switch network, that will be discussed. And we shall discuss about two basic approaches for controlling congestion. One is open loop techniques, another is closed loop techniques. Under the open loop congestion control techniques, we have two important algorithms. One is known as the leaky bucket algorithm, another is the token bucket algorithm. And we shall discuss a number of closed loop congestion control techniques such as admission control, weighted fair queuing related to admission control, resource reservation, or which is known as RSVP, then use of choke packets, load shedding, all these things we shall discuss. Finally, we shall close our discussion by considering a comparison between congestion versus congestion and flow control. And on completion of this lecture, the students will be able to explain the causes for congestion, understand the effects of congestion, what happens when congestion take place, understand various open loop and closed loop congestion control techniques such as leaky bucket algorithm, token bucket algorithm, and so on, which I have mentioned. Then they will be able to distinguish between flow and congestion control. So, with this background, let us start discussion about why congestion. So, here is the schematic diagram of a packet switch network. Let us have a closer look of a particular node. So, here I have considered a bigger view of a particular node. Let us consider node 1. This is the node 1. As we can see, node 1 has got 4 links coming from either the host or the station or connected to some other nodes. So, it has got 4 nodes, and also it has got some storage. How this storage is used? This storage is used to maintain queues. It can be considered as input queue and also as output queue, which stores the packets which are used as packet buffer. So, queue of packets are present on each node. So, here you have got queue of packets where the packets are buffered before they can be transmitted through the links. So, it has got 4 links. So, here is node number 1. Now, let us assume it has got certain queues, certain number of packets in the queues in this particular node. What happens in normal situation? In normal situation, a packet which is introduced into the network gets delivered to the destination if the network is not heavily loaded. That means all the packets which are entered from the station, say from station A into the network, which may be temporarily stored in this buffer, then it is sent to proper output link through some buffer, and then it is transmitted towards the destination. And in the last 2 lectures we have discussed about the routing techniques, how it is sent towards the destination we have discussed in detail. So that is the normal situation, but what happens when the traffic increases suddenly? We know that the data communication network is burst in nature. As a consequence, what can happen, suddenly the load can increase within a short period of time. What happens in such a situation? In such a situation, one situation is that these buffers may get filled up, and whenever there is no more storage available here, the packet gets discarded. That means when the buffer becomes full, there is no empty space in the storage, then the packet is discarded. That is one possibility. Another possibility is that whenever there is a big queue at the output node, say suppose it is going in this direction, and what can happen, the particular packet takes very long time to reach the front of the queue. That means for transmission, before it transmission, it spends long time in the buffer. As a consequence, delay increases significantly, and whenever delay increases significantly, what happens, the source node, after waiting for some time, does not get an acknowledgement. As a consequence, it sends and it retransmits the same packet, so which also in turn increases the load of the network. So these 2 things happen, and as a result, whenever the packets do not get delivered and delay increases to a large extent, then we say that congestion occurs. So congestion is arising because of heavy load in the network, and that can happen because of various reasons that we shall discuss once again. To summarize, what we can say that as packets arrive at a node, they are stored in an input buffer. If packets arrive too fast because of burst in nature, an incoming packet may find that there is no available buffer space. That is one possibility of a packet getting discarded. Another possibility is that even very large buffer cannot prevent congestion because of delay, timeout and retransmissions. As I have mentioned, one can argue that since the buffer space is insufficient, why don't you increase the buffer space? But that will increase the size of the queue, and the packet which is at the end of the queue will take long time to reach the front of the queue before it gets transmitted, and this will lead to timeout, lead to retransmission, and which will increase the traffic in the network, and which will, in other words, contribute towards congestion. Then the slow processors may also be responsible for congestion. Why? Because the slow processors may take very long time, although the link may be of high speed, but the slow processors may take very long time to process a packet. So it has to do the buffer management, it has to do some housekeeping, and for all these things the processors will take some time. If the processor is slow, that may take quite some time to do this processing. As a result, that may delay a packet and leading to congestion. Then the low bandwidth lines may also lead to congestions. As we know, the network may have links of various data rates or data line capacity, and as a consequence, if the bandwidth of a particular link is small, even that can lead to increase in congestion, because the buffer size will increase and the packet may not be delivered. So these are some of the common causes for congestions, and as we shall discuss, we shall see how these causes can be the effect of these causes can be minimized. So now we can define congestion. We are now in a position to define congestion. If packet arrival rate exceeds the packet transmission rate, the queue size grows without bound. That's what happens, and delay in delivery of packets lead to retransmissions. These two things, whenever these two things happen, the thumb rule says when the line for which the packets are queuing becomes more than 80%, that means if its original capacity may be 100%, but whenever it becomes more than 80% utilized, the queue length grows alarmingly. That means if the link capacity utilization of a link is increases more than 80%, that means the network has become overloaded, and we can say that the network is in congestion. So when too many packets arrive, a port, it will be port of the packet switch network, the performance degrades. This is known as congestion. So we can say that because of overload, delay increases, and the network is not able to handle the packets it has received, and as a result the packets do not get delivered to their destination, and this is congestion. And let us see what is the effect of it. So as you can see, this particular greenish curve, which corresponds to uncontrolled, that means no control measure has been taken for overcoming congestion. So in such a situation, initially as the offered load or the number of packets introduced in the network increases, all the packets get delivered, that means throughput, which is the packets delivered, follows linearly. That means if it is 0.2% of the total capacity, also it is 0.2%. So it rises linearly, but as you can see, when it crosses 0.6 to 0.8 mark, there is delay, and that delay leads to retransmissions, and as a result the throughput decreases, and the rate of increase decreases initially, then it suddenly drops, the throughput drops although the offered load increases, and at certain point it reaches, it becomes 0. That is known as thrashing situation. In thrashing situation, although the stations introduces packets in the network, but not a single one is delivered because of long delay, retransmissions, and various other problems, and that situation is known as thrashing. Thrashing occurs when the throughput becomes 0. Now ideally it should follow this curve if there is no congestion, but because of congestion it behaves in this manner, and by taking suitable congestion control approaches, the congestion can be controlled. Congestion can be controlled, and in such a situation the behavior of the network will be somewhat like this. As you can see, the throughput is less than the ideal curve. That means the throughput, because of the congestion control overhead, there is some overhead for implementing congestion control. So because of that overhead, throughput is less, because there are some overhead packets which are also transmitted, as we shall see, and because of that the throughput will decrease, but as you can see, it will not drop like the congested network, and as a result, as you can see, although the throughput rate is less, but it will never reach the thrashing situations. So this is the throughput effect of congestion on throughput, both in case of uncontrolled and controlled cases we have discussed. Now let us see about the other parameter, which is delay. Delay is a very important parameter, and as you can see, in the ideal situation, as long as the offered load is within the capacity of the network, delay is delay is very small, and that is delay is decided only by the propagation time and the transmission time. That is the only delay, plus the transmission time of the packet. There is no other delay in the network. However, suddenly whenever congestion occurs, whenever that the traffic is more than the capacity of the network, then of course delay will increase, because they will be buffered, and because of that delay will increase before, say, around 0.8% or so. Now, in the uncontrolled case, as you can see, delay can be very high compared to the ideal situation. So, you see the delay is very high in the uncontrolled network. On the other hand, by using control, although the overall delay increases, but the ultimately the offered, it can sustain very high offered load compared to the uncontrolled situation. So, we see that the delay parameter, how the delay parameter is affected in three conditions: ideal, uncontrolled case, and whenever it is the congestion control measures are taken, then how the delay is affected is shown in this curve. So, we have seen the two important effects of congestion, one on throughput, another on delay. Now, let us see what are the techniques that we can use to control congestion. So, basic principle, the congestion control refers to the mechanisms and techniques used to control congestion and to keep the traffic below the capacity of the network, and to keep the traffic below the capacity of the network. That is the basic objective of the congestion control. So, basic objective is to keep the traffic within certain limit such that congestion does not work, or whenever congestion works, you have to overcome it. That is why the congestion control technique basically can be categorized into two types. One is open loop congestion control, another is closed loop congestion control. You may be familiar with the control theory. This can be explained in terms of control theory. There are two basic techniques. One is open loop control, another is closed loop control. In the same way, the congestion control approaches can be divided into two types. One is open loop congestion control, another is closed loop congestion control. The open loop congestion control can be further divided into two types. One is based on source, another is based on destination. That means who does the control? It can be done by the source. That means source will try to control the congestion by introducing traffic in a controlled manner, or it can be implemented at the destination. Destination will take suitable measure. It will inform the source such that the traffic is reduced. So, who does the control? That is decided by the two different types under open loop congestion control techniques. Then under the category of closed loop, we have got two different types. As we know, in closed loop case, there is some kind of feedback. That means when the network is monitored and it checks whether control has taken place or not, which is not done in case of open loop case. In open loop case, there is some feedback from the system. There is some way of checking what is the status of the network, whether it is congested, how much congested, and so on. And so, in such a situation, there can be two different mechanisms. One is explicit feedback, another is implicit feedback. In case of explicit feedback, some of the nodes, usually switches on nodes, they will detect congestion, then inform the source or who can do the control, or who does the control. So, that means it will go to the either to the source or sources of the packets. This is explicit feedback. Another is based on implicit feedback. Implicit feedback is based on the fact that whenever a packet is sent, transmitted into the network, a particular source may wait for the acknowledgement, and by monitoring the delay in receiving the acknowledgement, the source may decide whether the network is congested or not. If the delay is small, which is essentially the propagation times plus transmission times, then we can say that then the source will say that network is not congested. On the other hand, its delay is high, very high. In such a case, the the source or the station gets some implicit feedback. That means that acknowledgement acts as a feedback, implicit feedback, which can be used for controlling congestion. So, based on this closed loop can be divided into two different types. Now, the the basic objective of the open loop congestion control is by adopting suitable policies such that the congestion does not take place in the first place. That is the basic objective. That means to prevent congestion, and as you know, prevention is better than cure. So, that is the policy for adopted in open loop congestion control. And for that purpose, suitable policies can be adopted while doing various of functions such as flow control. When flow control is being done, you know that there are various techniques used in flow control: stop and wait, then go back in, or sliding window protocol is used for flow control. Now, whenever you are using sliding window protocol, the number of packets in the network will depend on the window size. So, if window size is restricted to small numbers, say 7 or 3, then the traffic on the network will be small. On the other hand, if a large window size is used, number of packets in the network will be high before acknowledgements are received. And so, that flow control may help in preventing congestion. By adopting suitable flow policies for flow control, the congestion can be prevented. Then the acknowledgement policy, as you know, a particular destination node can send explicit acknowledgement packet which will reach the source node, source station. Another possibility is that whenever full duplex communication is going on, there is traffic in both directions, the destination node can send the acknowledgement in the form of piggybacking. We have already discussed the piggybacking approach. So, if piggybacking technique is used for acknowledgement, then the number of traffic in the network is less, it is reduced. That also help in preventing congestion. Then the retransmission policy. Retransmission policy essentially discuss the timeout interval. If the timeout interval is small, then many retransmissions will take place before acknowledgement is received. On the other hand, if the retransmission time is longer, that means the timeout interval is longer, there is a possibility that the number of packets, that means the acknowledgement is received before timeout take place. So, retransmission will not take place. So, that is why the retransmission policy, particularly the timeout interval, will help in preventing congestion. Then the caching policy. We have seen that there are two approaches whenever that automatic repeat request technique is used, that means for error control. We know that you can use either go back and ARQ, or we can use that go back and ARQ, or it can be that repeat request protocol. So, whenever it is repeat request, then we know that you have to do some kind of caching of the frames. So, whenever it is being done, then you do not have to retransmit a number of packets which have been received correctly by the destination. So, this caching also helps in reducing the number of packets in the network. Then the packet discard. The discard policy will also decide how the congestion control, whether in what way we shall discuss about it whenever we come across this packet discuss policy. And the routing techniques that we have discussed, for example, flooding increases the number of packets in the network. The traffic increases in a unbounded manner. So, if flooding is used for routing, then it may lead to congestion. So, by adopting suitable policy in routing, the congestion can be prevented. Now, let us consider two important techniques of open control, open loop control. One is the leaky bucket algorithm, another is token bucket algorithm. Here what is being done, some kind of traffic shaping is done so that the network is not congested. Say, let us see how it is being done. So, here it is, this is the basic philosophy. You can see here a bucket is getting filled up, and here you have got some kind of bursty flow, but output there is a fixed flow. And here whenever the bucket gets filled up, it spills over, leading to what is known as packet discarding. So, what it essentially does, Suppose the input is like this, input to the input packet generated by the source node is like this. Suppose it generates say at the rate of 10 megabits per second for 2 seconds, and then for 2 seconds it sends at the rate of 10 megabits per second. So here it is burst in nature. What the leaky bucket will do, it will generate, it will smooth out and send it at the rate of 2 megabits per second for 10 seconds. So for 10 seconds it is sent in this uniform rate. As a result, as you can see, the traffic is at a fixed rate throughout the 10 second period, and that is what is being done by this approach. So what it does, it shapes burst traffic into fixed rate traffic. However, it has the disadvantage that packets are dropped when the bucket is full. So when the bucket is full, the packets gets dropped in this particular type of algorithm. And another important drawback of this technique is that whenever the network is not congested, there are few packets in the network, even under that situation, it reduces the traffic, rather controls the packet in the same manner. So whether the network is congested or not congested, whether there are many packets or smaller number of packets, at a uniform rates packets are introduced, which is not necessary. When you have got fewer number of packets in the network, the packets may be introduced at a higher rate, and that is precisely what is done in this leaky bucket algorithm. So in the leaky bucket algorithm, the input is again burst in nature, and as you can see, as we have already discussed, the leaky bucket generates in a uniform manner. So this is the limitation. Even in the beginning, at the end, it generates at a uniform rate, and this limitation can be overcome by using the token bucket algorithm, as we shall see. So as I have already mentioned, they enforces rigid output pattern when even when the traffic in the network is small, that I have already mentioned. Now let us see what is being done in token bucket algorithm. In token bucket algorithm, the instead of controlling the it is done in a different way per each tick. So there is, you have got some kind of counter, and per each tick, say delta t, a token is added to the bucket, and whenever packets come, if you have got enough number of tokens accumulated, then it allows the traffic to be sent at the rate in which it has come. On the other, after all the tokens are exhausted, then however it will introduce the packet at the rate of 1 token per tick. That means it will become same as the leaky bucket algorithm. So let us consider the same example. Suppose it has received at the rate of 10 megabits per second for 2 seconds. This is 1, this is 2, and because of the burst nature of traffic. In case of token bucket, what will be done? Maybe for 1 second it will send at the rate of 10 megabits per second, and assuming that 5 tokens were stored, and after that, of course, for 5 more seconds. So this is 1, and then 2, 3, 4, 5 remaining, rather it will take 6, because 5 more, 1, 2, 3, 4, 5. So for 5 more seconds, that means in 6 seconds all the packets are transmitted. So as you can see, initially for this part there was accumulated tokens, and because of that the data is transmitted the rate at which it has been introduced into the network, and after that it is transmitted. Both this leaky bucket and token bucket algorithm can be implemented by the operating system or by a network interface card which is connected to the network. And as you can see, it is implemented with the help of a counter which is initialized to 0 in the beginning, and then per each tick the counter is incremented. On the other hand, whenever a packet is sent, then the counter is decremented. In other words, countdown is performed for each packet sent, and count up is performed for during each tick, and in this way this counter is maintained to implement this token bucket algorithm. So it can be implemented either by hardware or by the operating system of the host. So we have seen that the token bucket algorithm saves up to a maximum of n tokens and allows a vastness of n packets in the output stream, thereby giving faster response. We have already seen that the time taken for introducing the packets in the network is small. I mean, time taken is smaller than the leaky bucket algorithm in token bucket algorithm. So it increases the throughput compared to the leaky bucket algorithm. So it provides you better throughput. Now, to make the traffic shaping approaches successful, it is necessary to specify the requirement in a precise manner known as flow specification. That means the traffic shaping can be done very effectively if the specification, flow specification is provided by the source node in a proper manner and its requirement is specified in a proper manner. What are the things to be specified? Let us see. First one is input characteristics, that means the maximum packet size in terms of maybe kilobits or megabits, whatever it may be. Then the token bucket rate, it can be say megabit per second. Token bucket rate, the maximum rate at which the packets can be sent. Then token bucket size, it can be megabit or megabyte or gigabyte, and the maximum transmission rate that can be done. So these are the 4 input characteristics to be specified. And the other hand, the services required, the desired by the host must also be specified. What is the reliability desired? What is the delay in sending a packet is desired? Delay means what is the delay it can tolerate for a particular application, that has to be specified depending on the nature of traffic, whether it is data or voice or video, the delay has to be specified. So whenever you are sending voice or video, another important parameter, it is not the delay but the variation of delay, that has to be specified properly. So this variation of delay needs to be properly specified, that is expressed in terms of jitter. Then also it is necessary to specify the bandwidth required for a particular application. So obviously for sending speech or or music, the bandwidth required is smaller compared to bandwidth required for sending video. So these are the services desired must be specified so that the traffic shaping can be done properly. So with this we come to the end of the open loop discussion, open loop congestion control techniques. Now let us focus on the closed loop congestion control techniques. And in closed loop congestion control techniques there are 3 basic steps. First one is monitor the system for detection of congestion. That means the monitoring of the status of the network is necessary, and usually it is done by the nodes or the switches. They will monitor and decide based on the delay, based on delay, based on queue length and various other parameters, and then that has to be informed to the place where the action is taken. That means pass the information to proper place for taking action to control congestion. Usually this action has to be taken by the stations or the source nodes. So, information has to be passed on to the stations for taking action to control congestion. Then the source node will adjust system parameters to get out of congestion. So, that means the closed loop congestion control techniques are used when the network is really in congestion, maybe lightly it is in light congestion mode or heavily congested, whatever it may be, both will be detected. And there are various approaches used for congestion control. First, let us consider the admission control. This admission control technique is used in virtual circuit networks. So, when congestion is detected, no more virtual circuit is allowed to be set up. That means, whenever a congestion has already taken place, the network will not allow to set up any more virtual circuits. That is the basic approach of this admission control. This is one policy. Another is virtual circuit is allowed to be set up around the congested subnets. That means, maybe the congestion has affected or the traffic has increased significantly in one portion of the network, not throughout the network. So, if the packet can be sent around the congested subnet, not through the congested subnet, then also this is also part of the admission control. That means, the virtual circuit is allowed to be set up around the congested subnet, not through the congested subnet. That can be done as part of the admission control. So, an agreement between a host and a subnet is negotiated when the virtual circuit is set up, so that resources along the path are guaranteed throughout the session. That means, whenever a virtual circuit is set up, the required bandwidth, required buffer space, these are all negotiated between the source node and the subnet, so that the congestion is overcome. So, this is the admission control approach. However, this may lead to underutilization of the resources. Since the virtual circuit, the source node is negotiating and some kind of allocating some of the bandwidth and resources, even when it is not utilized because of vast nature of traffic, it is underutilized. That is one limitation of this admission control approach. Even under the availability of resources, the virtual circuit is not allowed to be set up. So, this may lead to underutilization, but definitely it helps in overcoming congestion. Second approach under the closed loop control technique is closed choke packets. So, this approach can be used both in case of virtual circuit as well as datagram type of networks. So, each node monitors the utilization of the output line. So, this is based on the utilization of the output line, as we have already mentioned that as a thumb rule, whenever the utilization increases beyond say 80%, we may consider that network is congested. So, whenever this kind of utilization increases beyond some limit, beyond some threshold level, and output line enters a warning state. So, the particular line enters a warning state. So, if the output line is of a newly arriving packet is in warning state, a control packet called choke packet is sent from a congested node to the source stations. That means, the congested the node to which a link is connected and which has reached a warning state, that sends a choke packet towards the source node. So, the original packet is tagged so that it does not generate any more choke packet. So, although a choke packet is sent towards the source node, the node forwards the packet towards the destination. So, it may be possible that the other nodes in the path may again send choke packet to prevent that it is tagged, so that no more choke packets are generated. So, after receiving a choke packet, the source station reduces traffic by certain percentage. Suppose after receiving a choke packet, the traffic is reduced by 50%. A station reduces traffic by 50%. Now, after reducing the traffic for 50%, again it waits for certain duration. Still, if it receives a choke packet, it further reduces by 25%. After waiting for some more time, even if it receives a choke packet, it reduces by another 10%. So, in this way it goes on until and at some point of time it may discard packet, but usually whenever this kind of reductions takes place, the network will come out of congestion and no more choke packet will be received. So, if no more choke packet is received for certain duration, then the traffic is again increased, but not at a high rate. Maybe it is increased at the rate of 10%. So, it is increased at the rate of 10%, but reduced at a higher rate in the beginning, then the rate is made smaller and smaller. So, this is how the traffic is controlled by the source node in response to choke packets, and the system comes out of congestion. This choke packet approach has one serious drawback, that the action taken by a source is voluntary. That means a source node after receiving a choke packet may decide to reduce the traffic or it may not reduce the traffic. So, to get around this problem or to overcome this problem, pair queuing approach is done. Algorithm is used where queues are scanned in round robin manner, and then packets are sorted in order of their finishing time. So, you can see these are the first byte by byte scanning is done, and it is found out, the finishing times are found out. For example, 6 is the finishing time for queue for this packet on the input line B, then the 10 is the finishing time for queue for the packet on input line C, and so on. Now, after finding out the finishing times, then the packets are ordered in this manner in order of finishing times, that means B, C, A, D. Then the packets are said in that order, first B is sent, then C is sent, then A is sent, then D is sent. So, this is known as pair queuing. So, this is based on the queue length. Another possibility is that it can be based on the application. For example, for some application it may be necessary to discard a recent packet. For example, if it is based on, say, it is sending data. In case of data, it is necessary to discard a recent packet rather than an old packet. The reason is, if a recent packet is discarded, if the recent packet is not discarded, if an old packet is discarded, then again you have to perform retransmission of a number of packets by using go back and air queue. On the other hand, if a recent packet is discarded, then the number of retransmissions will be reduced. On the other hand, if it is a, say, video or voice, in such a case it may be necessary to discard an old packet rather than a recent packet. The reason is, old packet is no longer important. It may have already caused some damage, some kind of jitter in the system, but if a recent packet is not allowed to be discarded. So, some weights can be assigned based on the application, either so that the packet discarding policy can be formed, and this may lead to weighted fair queuing. So, based on these applications you can do weighted fair queuing. Some weightage is given to different packets based on different applications. Then as I was mentioning, packets are to be discarded, and when other methods fail, the nodes can resort to the heavy artillery known as load shedding. That means whenever the nodes are not able to handle the packets, the buffer is full or delay is too high, in such cases packets can be discarded. Now, one possibility is that a node drowning in packets may use at random discard policy. That means it may discard packets at random, and however, this at random policy is not good. In many situations, some packets are more important than others, as I have already mentioned. In such a case, intelligent discard policy can be adopted. Some intelligent discard policy can be adopted based on the application, and the application must mark the packets with priority classes. So, when in such a case, instead of discarding packets at random, using the intelligent discard policy, the packets with lower priority are discarded than packets of higher priority. So, this approach is known as load shedding. The terminology or the word has been taken from the electrical distribution system, where, as you know, whenever the load on the electrical network is high, load shedding is done, and this approach is similar to that, and here essentially packet discarding occurs. And simulation results show that it is better to start discarding packets early rather than wait until the network is completely clogged up. That means question arises when packet discarding should start. Simulation result has confirmed that it is better to start discarding in the beginning or in the onset of congestion rather than when the network is heavily congested. That means whenever the discarding is performed early in the early phase of the congestion, then it may lead to it may come very quickly out of congestion, but whenever it is already congested, then its effect is lesser. Then we shall discuss about another important technique, which is known as resource reservation protocol. This is particularly important in the context of multicast applications. So far we have discussed about point to point data flow. That means there is a source, there is a destination. Traffic is going from source to the destination. It is essentially point to point between two nodes. But there are many applications where the data has to go to multiple destinations, or it has to be broadcasted. So, whenever it is necessary to whenever a packet has to go to multiple destinations, we call it multicasting. And multicasting application, one important application for multicasting, for example, there is a station who is giving video service. That means video on demand service to a number of users. So, depending on the network, a group of people will ask for video services from a particular stations. It may be the same video has to go to a number of stations depending on the requirement. So, in such a situation, this is useful. So, in such a case, each group is assigned. First of all, it uses multicast routing using spanning trees. So, let us see how it is being done. Here 1, 2, 3, these are the sources, and the this 4, 5, 6, these are the destinations. Now, these 1, 2, 3 are giving video service to the destination stations 4, 5 and 6. So, each source will form a spanning tree, as you can see. Here the spanning tree is from this station, it will go to node A, then it will go to node C, then it will go to node D, and from there, as you can see, it is going to three different sources, 3 different destinations. So, it is transmitted on 3 paths rather than 1, and this spanning tree is based on the least cost path, as you can see. So, from 1 to 4, 5, 6, this is the spanning tree. Similarly, the spanning tree can be from 2 to again 4, 5, 6. Now let us see how this resource reservation can be done. So, suppose 4 wants some service from the source 1. So it will reserve resources along the network, the bandwidth and the data rate that is required. After that, another destination node may decide to the same node may decide to have another video from another source. So it reserves the bandwidth, then bandwidth and the buffers for in different nodes along the path. Now at this point what can happen, say another destination may also want to have the reserved resources along the path. Now you can see here between C and D, this 4 has already reserved for 2 video streamed video traffic, and at the same time 6 is demanded another one. Now if the nodes between C and D has to find out, the C and D has to find out whether there exist enough resources between C and D, and only then it will allow destination station D to set up the virtual circuit. So we find that in this way the resources are reserved before the transmission of data takes place, and this is particularly in multicasting application this is very important. Another possibility is that it may be necessary to broadcast some information to a number of stations, number of destination stations. So in such a case, one important candidate for broadcasting is flooding, as you know. So although flooding increases the traffic significantly, but for broadcasting purpose, when broadcasting has to be done, the flooding is used for the purpose of sending broadcasting. Finally, we shall discuss about the difference between congestion and flow control. People are confused about these two techniques, congestion control and flow control. We have seen that in both cases the destination nodes sometimes send a packet towards the source node, either for flow control or for congestion control. As we have seen, choke packets are sent. That is why people gets confused about these two techniques, but they are much different. As you can see, congestion control is a global issue. It is a joint responsibility of the users and the network. That means so far as the congestion control is concerned, not only the stations, all the nodes, all the stations are responsible for the congestion control, for the congestion to take place, and it occurs because of combined behavior of the stations, switches, routing policies and so on. We have already seen when congestion occurs. Its job is to ensure that the subnet is able to carry the offered load. Let us take an example when congestion can occur. Suppose you have got 1000 nodes and they are sending at the rate of 1 megabits per second. So in such a situation, when all of them starts sending at that rate, at maybe lower rate, say 1 megabits per second, congestion will occur. On the other hand, flow control is a local issue between a sender-receiver pair. It is not a global issue. See, the source-destination pair or the sender-receiver pair is responsible. Its primary function is to ensure that a fast sender does not overwhelm a slow receiver. That means flow control is necessary in such a situation. For example, there is a server which can send at the rate of 10 gigabits per second. On the other hand, a destination node which is a desktop can receive only at 1 gigabit per second. So in this case it will get overwhelmed. Although there is no heavy traffic in the network, a source node with heavy load can overwhelm a receiver. So in such a situation, flow control is performed. So we have discussed the differences between the congestion control and flow control. Now it is time to give you the review questions on this lecture. First question is, what is congestion? Why congestion occurs? Second question is, what are the two basic mechanisms of congestion control? Third question is, how congestion control is performed by leaky bucket algorithm? Fourth question is, in what way token bucket algorithm is superior to leaky bucket algorithm? Fifth question is, what is choke packet? How is it used for congestion control? Now let us give you the answers of questions on lecture number 21. First question was, in what way random routing is superior to flooding? As we have discussed, the random routing significantly reduces the number of copies of a single packet to be transmitted through the network compared to flooding, but has the same level of simplicity and robustness of flooding. That means the random routing reduces the traffic, but has the same characteristic of features like simplicity and robustness of flooding. That is why random routing has some advantage over flooding. Second question was, why adaptive routing is preferred over static routing? We have seen that adaptive routing increases the traffic in the network. However, adaptive routing is preferred because of some advantages. First advantage is that it improves performance and it works under changing conditions. What are the changing conditions? When there is a node failure, node or link failure, or there is congestion, then this adaptive routing will help in adding congestion control, which the fixed routing cannot do. Third question was, what are the limitations of adaptive routing? Answer is, routing decision is more complex in adaptive routing, which imposes more processing burden on the switching nodes. As I have already mentioned, the routing algorithm used in adapting routing is quite complex. As a result, it imposes burden on the switching nodes, and the traffic overhead is more in adaptive routing. We have seen that in adaptive routing we have to use some additional packets for control purposes. That is why the traffic increases. If adaptive routing algorithm reacts too quickly to changing network state, it may lead to congestion producing oscillation in the network. As I have already mentioned, whenever adaptive routing is used, if it is performed very quickly, then the traffic is sent to another part where congestion occurs, and again the traffic is sent to another part. So that means the congestion area keeps on changing, and that is why it leads to congestion producing oscillation. So these are the limitations of adaptive routing. Fourth question was, compare and contrast distance vector routing with link state routing. Answer is, distance vector routing uses the knowledge about the entire network, routing only to neighbors, information sharing at regular interval. On the other hand, link state routing has knowledge about the neighborhood, routing to all, information sharing at the regular interval. It converges quickly, requires more CPU, power and memory, more scalable. Then in what way second generation ARPANET algorithm differs from first generation? As you have seen, in second generation delay was actually measured rather than the queue length. That was the basic difference between the second generation of the first generation. So friends, with this we come to the end of today's lecture. Thank you very much.